So this part is our another algorithm to be used for this time's final project. So not only for doing the QoS, we're also trying to just like integrate the LDDoS algorithm, defense algorithm for our network processors. So the key idea after researching the papers, the LDDoS defense is a way that be used to just like for defense the DDoS attacked from the long period but just a low frequency server request for trying to attack the server and crash the server. So because our backend is still just like haven't some bug didn't finish yet. So for now, we are just like using some software to just like to do the simulations, and in the future, we are going to just like in the later times, we are going to just like integrate this one into the network processors. So this algorithm, we just like we can simply be divided to be like the about five phases. The first part is for just like packet capturing, which is like this part, which is about from this part. Because this one should be just like if later should be implemented by the network processor, but for now I'm just like for some test cases where I'm going to just like directly use some like command for read bcaps that to get that government to get some like the information for our packet capturing. So after we capture the packet, get the pcaps documents, we start our phase two, which is do the samplings to divide the total time range into equal length intervals. For example, like every 1 milliseconds, and count how many packets arrive for each intervals. So in that case, we can produce a time series representing the traffic intensity over the time, and then after we get that sampling analysis, we do the autocorrelation analysis. So we should measure how similar the time series is to a delayed version of itself. So the reason we do that is that because the periodic signals like the LDDoS it's not like the normal DDoS attack, which have like the high frequency. We can find like the larger amount of the server requests in a short time period, so we can detect it. So, but in the LDDoS one, there are a long time period which is hard to be detected. So we use this method to get the periodic signals that which will show the strong correlation at regular intervals, and also, if that one is like something like the normal usage package, those random traffic will not show such correlations. So that's why we do use it this way. And after we get this part, we do the DFT, which is discrete Fourier transformations to convert the autocorrelation output into the frequency domain using FFT. So this will revolve the energy distribution across different frequency. So in that case, because the reason we're doing that is because LDDoS traffic, which is being periodic, like I just said, which could produce a strong frequency peak in the low frequency range. But the normal traffic speed, the energy across just like will not produce something like that one. Then after we do those kind of analysis, we do the last phase, which is the power spectral density analysis. So for doing this one, the analyze the output of the DFT will produce to a power spectral density graph, so which we could examine whether energy is concentrated in the low frequency bands. If it is, we do the flag to a potential LDDoS attack for showing, say, oh, be careful, there is an LDDoS attack. That's it for my part all about the LDDoS situation. But in this one is we're still doing some bug fixing and just like testing, simulation testing. In the later weeks, we are going to just like integrate this one with the QoS algorithm to see if that one could get like the better performance. Thank you so much.
So this week, I researched on the quality of service implementation on different routers, and found out it's basically that you give specific package coming from a specific source IP and source port to or a package that's going to a certain destination IP or destination port or both priority, so that the router routes this package first over the other package to maintain a level of service for the application that's running on the client side that needs priority and the quality of service. And in order to figure out which package needs priority, I wrote a module called QoS identification. Basically, it contains a register file called QoS list that will contain entries of IPv4 address and the port number that the software will write into a register, and so that we can give priority to this specific address and port number in the even if it's either source address needs priority or destination address needs priority case. And these inputs are responsible for writing to the register file. And there is also a flag called URG in the TCP header that is responsible for, according to the Wikipedia, that is responsible to indicate that the package is urgent. And in my understanding, that means that it also will need priority. And so that basically this module will compare the current package source IP address and source port, or the destination IP address or destination port, with the entries in the QoS list register file, which these two will be inputted. It will be contained in the source IP and destination IP will be contained in the IPv4 package header, and source port and destination port will be included in the TCP package header or the UDP package header. And so it will be concatenated with 2 bits of 11 or 10 to indicate that to match with the entries that will be in the register file, since the register file needs a valid bit and a bit to indicate whether it's source address or destination address that needs priority. And in here is the test bench I wrote for the module. Basically, it will first reset everything, and then it will write 2 entries into the register file called QoS list, with always the first bits being 1 meaning valid, and 0 and 1 for the destination IP and source IP needs priority, and then it will be the IP 32-bit IPv4 address that's being represented in 8-bit, 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 and 8-bit style. And lastly is the 16-bit port number. And then after we finish writing, we will set the list write enable to 0 and begin cycling through port source IP and destination IPs and source port and destination port to see if package needs priority. Then the this module will have its output QoS priority be 1, either if this match is true or the flag URG is 1 on the package. And let me rerun the simulation. Here we can see that first is reset, and this resets all the entry in the QoS list to 0. And then first cycle it writes this into the entry 0 and then entry 1 the next cycle. And then the IP source IP and destination IP began to change with source IP, destination IP, and source port. Source and destination port began to change together with let me see. Internal noise output input port together with the source IP and destination IP. So that source IP and destination IP also changes, and that only so in this case there's no match from the source IP or destination IP and the port number to the so this and this will format will be concatenated into the source comp in here and here, so that we can see that there's no match here, but the flag is high in this period here, so that the priority is true over here. And here we can see that this entry 3C0880164017 matches with this entry in the QoS list, so that it's also given priority, as the QoS priority output is 1.